Hey guys, this is notes for 8.3. We're actually going to do a worksheet as opposed to the textbook. I've looked at this, I've talked about it for years, and as I look at it, I don't think there's any way to start this other than to say, first, video is going to be a little bit longer. It's going to take us time to get through some things. So bear with me. But second, guys, we got to put on our big kid pants, all right? We're going to start shifting. We've got to be able to do some more complicated algebra, understand some pretty big ideas. So I'm going to actually start with the end in mind, okay? So first off, let's start with, I'm going to look at question number 10 here. I want to simply graph this equation. Now notice you have x's on top, you have x's on bottom. There's a lot going on. This is a complicated looking problem. At least it should be. We're taking basically a function, a cubic function, and dividing it by another cubic function. And what does it end up looking like? Now I've pre-typed all this in. Now I got to put parentheses around the numerator, parentheses around the denominator, being real careful here. You can see how I've typed all this in, 2x cubed minus 2x squared. That's all in one set of parentheses, divided by new parentheses, x cubed minus 9x. All right, now if I hit graph, some of you might be expecting some sort of a curve, sort of like the polynomials we've graphed in the past. Some of you might think, oh, it'll be like a line. It'll be a solid number because x cubed divided by x cubed, things like that. If I hit graph, this is what I get. This graph is broken into several pieces. I see 3. But inside that, there are even issues that exist within those 3 solutions. Questions like, where is it that this graph breaks, right? Because you can see this graph's going up forever, and then all of a sudden it comes from down in the negatives. So where is this break? There's another break over here. Where does that happen? Other questions like, does this flatten out as it goes to the sides, or does it like keep going down forever? Does it flatten out and stay the same? Where does it cross the x? Does it cross the x-axis here, or does it just touch and turn back around? Those are all meaningful questions that I would like to be able to answer about this specific problem. To do that, I'm going to need some specific information. And we're going to learn about how to find this specific information, okay? And so we will come back to this problem here in just a second. Okay, but let's take a second and put kind of a couple of ideas together from this graph. Okay, so if this was our x and y axis, this is not going to be pretty, but it's going to be something like this, and then this guy's in the middle, right? So there are these breaks that happen like this. Oops, it should be between them. We're going to call these vertical asymptotes, okay? Because they're vertical and they're those dotted lines that we graphed before. This will also have a horizontal asymptote. The question, will it flatten out or will it die off? Will it drop really low? It is going to flatten out. And just like our exponential functions, it's going to flatten out as it goes to the edges, both on the left and the right. It's going to try to follow this asymptote forever. Those are things that we'd like to figure out. Where are the horizontal and vertical asymptotes for this graph? Also, does it ever touch the x-axis? If it ever does, now this sketch is a really crappy one, but if it ever touches the x-axis somewhere, I want to know about it, okay? I want to know, does it have any zeros? And, of course, we've got to give ourselves a domain. On these vertical asymptotes, we're going to not be able to have a value there, so we want to be able to give the domain for that. We won't worry about the range for these. It's pretty complicated to get exact values for the range, but we will give a domain for these. Okay, so that being said, how do we figure out all this stuff? So I'm going to walk you through one example with this problem, and I'm actually going to go back up. We have a note catcher up higher on here that you should have gotten. And hopefully that note catcher can help you say, okay, what do we mean when we say holes? What do we mean when we say vertical asymptotes? Things along those lines. So bear with me. We're going to go find all this stuff out together right now. And the steps I'm going to take you through, some of them won't apply to every problem, but if you use them, it'll help you solve every problem. All right. First thing that we always want to do is factor the top and bottom equations as much as we possibly can. There are 2 types of factoring. There's what's called Gcf factor, and then there's the 2 sets of parentheses factor. Okay, GCF means there's something in common. Both terms or all three terms have something in common. For instance, right here, you could see that both of these two terms have a 2 in them. So I could pull that out, and that's a good idea. So I'm going to pull a 2 out. But they also both have x's in them. And I want to pull out my x's that I can as well. Now this has x cubed, which means there's 3 x's, but this only has x squared, which is 2 x's. The most I could pull and still pull the same from both of them would be x squared. And I'd have to say, what's left behind? Well, 2x squared times x produces 2x cubed. Think about the foiling, or the distribution, right? And then 2x squared times a negative 1, right, would be the negative 2x squared. See, if I pull the 2x squared out, I have to leave something behind in each of those positions. That's called Gcf factoring. Next, okay, we look at the denominator. And this has, again, sort of a Gcf factoring. We can see the x that's in common. So if I pull that x out, that leaves me with x squared, because x cubed, take an x out of it, you get x squared, minus 9 if I take the x out of that. A lot of times this is where we'll stop, but we always need to look at our x squareds and see if we could factor that as a parentheses. See this x squared minus 9? Yeah, that tells me that there's more to do, because that's a difference of squares. So I'm going to replace this denominator with my x. That's still there, but I think x squared minus 9 factors as x plus 3 and x minus 3. All right? Okay, now that we have it factored, we can find everything that we need, but factoring was important. It had to happen first. And if you're struggling with the factoring, watch the videos, look at some of the solutions, and see if you can figure out why is it that we're getting certain results. Okay? Come and talk to me. All right. First thing we're always going to look for are vertical asymptotes. Oops, vertical asymptotes. And those come whenever the denominator equals 0. So I'm looking at my denominator saying each time I see an x, I want to know what would make that portion of the denominator equal 0. So you can think about these three things. You got x times x plus 3 times x minus 3. And if any one of those three pieces is 0, I have a vertical asymptote. So I'm going to say that there's one at positive 3. That's from this guy right here. Then I'm going to say that there's one at negative 3. That's one from this guy right here. And you might not remember, but whenever there's an x by itself, okay, that doesn't have the plus this or minus that, we always default to a 0 for that. So this means in my graph, I should have vertical asymptotes at positive 3, which if you guys remember the picture from our calculator, that seems familiar. There was a break there, and there should be a vertical asymptote here at negative 3. We saw those. We didn't see it at 0. If you look back at the calculator, it doesn't look like there's a break at 0 right here, but there is something, like it looks like it's hitting the axis. Like I'm not sure what's happening here. If you look at the table, the reason we have vertical asymptotes is because they produce errors. You can see there's an error at negative 3, an error at 0, and an error at 3. The reason there's an error is because the equation is asking us to divide by this number, and it turns out this number turns the denominator into 0. Well, dividing by 0 is undefined in mathematics, and so we don't have a solution for it. So we have to jump it. We have to break that line. To talk about why there's not a vertical asymptote at 0, we have to talk next about holes. Sometimes a graph is cruising along doing its own thing, and then suddenly there's one value we can't use, and we just keep trudging along. And we'll put a hole in the graph rather than a vertical asymptote. Well, why do we put a vertical asymptote? Why do we put a hole? What's the difference between the two? If in the problem it is reducible, meaning we can divide something off, that becomes a removable discontinuity or a hole, and we can get rid of that. So let's take a look at this piece here, this x squared, and this x down here. Can we divide x squared by x and get a clean result? Not like some fractional weird result. Like, does it divide evenly? The answer is yes. This would go to would cancel, and the x squared would become a regular x, right? Because you have x squared, you take one of them away, you get x. So that meant that 0, the value that came from this x, was a removable discontinuity, and so it will fit in the whole category, not in the vertical asymptote category. What that means is wherever I hit this, whether it's up here or down there, wherever it is, there's going to be a hole in the problem, okay? Now normally that just depends on where am I at that point. We'll find out this has a special case where it's actually on the axis. It doesn't usually happen on the axis, but here it does, so it's fine. Let's keep going. Next thing we're going to look for are, we're going to go ahead and state the domain. Okay, the domain of the graph is that x cannot be any of these values above. Cannot be a vertical asymptote, cannot be a hole. And so we're going to say it cannot be 3, -3, or 0. Now, you saw that in the calculator when we looked at the table. There were errors on those 3 values. That's what we're basically saying. Hey, these are where your errors will occur, so don't use them as x's. They won't work. All right, next we have what are called horizontal asymptotes. We want to know, where does this graph flatten out at? Well, there are 2 types. And again, the note catcher will help us with this a lot. There are 2 types. We're going to go back to the original problem. There's what's called balanced, and there's what's called bottom heavy. Those are the only 2 types we'll ever look at. Balanced means that the exponent for our first x matches the exponent for our first x top to bottom. Notice these are both x cubed. This is an example of balanced. Whenever it's balanced, we use the leading coefficient test. So whatever numbers lead the equation, this would be 2 over 1. So my horizontal asymptote would be at 2. That means if I go up to 2, I can draw in the horizontal asymptote. Okay, we're almost there. We're almost there. After we've canceled out our discontinuities, we want to know, is there anywhere that it would still equal 0? Okay, is there anywhere where we would hit the x-axis? These are the x-intercepts. Where are we going to hit the x-intercept or the x-axis? And that comes from the top being equal to 0. Just like we had the denominator equal to 0 gave us vertical asymptotes, the top being equal to 0 gives us our x-intercepts. So over here we have an x that's by itself. That would mean that there's an x-intercept at 0. And over here there's an x minus 1. That means positive 1. I should have a spot at 0, which means I would hit the axis right here. I should be hitting the axis there at 1. I should also be hitting it here at 0. And normally we just put that dot and we go to town and it was like golden. But because it's also a hole, we're going to put an open circle there. Yeah, we're supposed to hit the x-axis there, but technically we can't because it's a domain restriction. And so we're going to avoid hitting that altogether. Okay, now that we have all 5 of those steps done, we can draw a sketch of the graph using our calculator to fill in the gaps. I would still always put these in Desmos or put them in a graphing calculator just to make sure that I'm seeing what I think I'm seeing. All right, I'm going to grab a different color here. Let's go with fuchsia, and yeah, that'll work. Okay, the graph on the calculator has something up above on the top left. Now that's going to stay above the horizontal asymptote. Horizontal asymptotes can be crossed, but that's very rare, and it only happens usually when we're crossing through the x-axis. Otherwise, they typically don't cross. So I'm going to follow that and curve up and follow this asymptote. So I've got this piece. I noticed there was a similar piece over here on the right following these 2 asymptotes. In the middle, it does get a little funky because the graph's going to try to follow this asymptote, and then it's going to have to curve over to get to the x-intercept. Now, I pass through there, and then you can see how it's kind of flat, and then it comes back down through that other x-intercept. And there's my graph. Now, again, that's a really crappy graph because I'm using a mouse to do it. But if we look at what we had on the calculator, what we have in front of us, those are pretty good that's a pretty good representation of the information. And if I zoom in just a bit around the middle, you can see how it's coming through, it's crossing, it's coming back down through 1. we could keep zooming in here to 0 over and over and over again, and we would never be able to get small enough on a calculator to see the discontinuity or the hole. And so you have to know those things exist from the equations themselves. All right, I'm going to stop this video. This is a video of what you're doing on your entire assignment here. But then I'm going to do another video that goes through a couple other, or goes through the note catcher as well. So if you guys are going to have questions, I know it'll happen. Graphing calculator is going to help a ton, but you need to find the vertical asymptotes, holes, domain restrictions, horizontal asymptotes, and x-intercepts for every single one of these. It always starts with factoring. You factor first. GCF, if there's a common factor, factor it. If there's not, you're looking for double sets of parentheses type of factoring. You're just going to have to look at each problem on its own and see how it works out, okay? All right, good luck, and I'll see you guys in class.